Hi, in this video I would like to go over something that is called the Pascal's triangle, and from there I will transition to a very popular question type, which is called the binomial expansion. Okay, so let's get started. So Pascal's triangle it's something that's pretty cool, right? And it's relatively easy. So let's just take a look at what a Pascal's triangle is. So I'm going to start with 1. And the next line, I'm always going to start with 1 and end with 1. So the next line, I'm going to start with 1. And the value that I'm going to have here comes from the two values above it. So 1 plus 1 gives me 2. Okay? And then I'm going to end with 1. So next row, start with the 1. 1 and 2, that gives me a 3. 2 and 1 gives me a 3. And with 1. So I'm just going to keep on doing that. So that gives me a 4, a 6, a 4, a 1. And that just keeps going. Okay, so this can go on forever. I'm not gonna do that, of course, and we can just keep doing this. Okay, now this is called a Pascal's triangle, and which can be constructed pretty quickly on the spot, and it's actually very easy to make it. But what's so cool about this? A few things. Let me highlight them for you. First, you see that I already mentioned this. We always start with the 1 and we always end with the 1. And also, the numbers kind of repeat itself. So 1, 2, 1, that's not very obvious. But you see here, I have 1, 3, and then I have 3, 1. Right? I have 1, 4, and then I have 4, 1 with a 6 in the middle. Okay, so 1, 5, 10, 10. 1, 6, 15, 15, 20. So you see that there is some sort of symmetry. We sort of have a mirror in the middle where we can find the exact same value on the opposite side. Right? So the symmetry is something that that's pretty cool, and sometimes that symmetry can help us to solve questions as well, but we will talk about that later on. All right, so that's what a Pascal's triangle is. Now, how can we use Pascal's triangle in math problems? So let's do one. Let's say today I need to, let me change your pen. I'm trying to expand this. Let's say x plus y, say, cube. So in the past, we will have to do this. X plus y, x plus y, x plus y. And then we should expand each one of them one by one. And, you know, for the FOIL method. But I'm not going to do that. Okay? I'm not going to do that. Instead, I'm going to use my Pascal's triangle to help me out. So, I have power of 3. That means I'm going to be looking at this part. Okay? This is my, I'm going to, for now, I'm just going to write down this is my n is equal to 3. Okay? And so this will be, let me write it on the other side. This is n is equal to 3, n equals 4, n equals 5, n equals 6, so on and so forth. You might be wondering what's that n? You'll see. Okay, you'll see what does the n represent. So, you know what? Let's do it the old school way. So x plus y cube will give me, I can break it down into x plus y squared times x plus y, right? So x plus y squared is easy. For those of you who remember the formula, that would be x squared plus 2xy plus y squared multiplied by x plus y. So now I have no choice but to FOIL it. So x times x squared gives me x cubed plus 2xy plus y squared x, and then I'm gonna FOIL the y as well. So that will give, so if I x squared times y gives me x squared y, x squared y. Wait, I think I made a mistake somewhere. Okay, let me undo that. Sorry. Okay, so from here, oh, I see the mistake here. This is plus 2xy. Okay, there you go. So now everything's good. So that's gonna give me, if I FOIL it, I'm gonna have x cubed plus 2x squared y plus xy squared, and then do the same thing for my y. That will be x squared y plus x squared y plus 2xy squared plus y cubed. Okay, so I can clean this up. I'll get x cubed plus 3x squared y, 3x squared y plus 3xy squared plus y cubed. All right, I'm gonna highlight a few things here, and you're gonna find something that is almost shocking. Okay. Now, before I highlight the stuff, I'm gonna add a few things. So, what is the coefficient in front of my x cubed? It should be 1, right? But normally we don't write the 1. But for now, because I want to show you guys something shocking, so I'm gonna show that 1. Okay. So I'm gonna put the 1 there, but normally we don't, right? So let's take a look. I'm going to highlight the 1 here, highlight the 3, and the 1. And I want you guys to look at this row when I said n is equal to 3. 1, 3, 3, 1. 1, 3, 3, 1. Isn't that cool? So, the Pascal's triangle is very super useful in terms of giving us the coefficient of the respective term. So what do you think? What do you think the n equals to 3? What I have here, what does that represent? That simply represents the power, the exponent that we're trying to expand here, right? So if let's say if I had, instead of 3, I have 13. Let's say if I have 13, then I will have to do this all the way down to n is equal to 13, which will take us some time, right? But of course, we can get there, and there is actually another way, another method for us to do this without actually creating or completing the Pascal's triangle to n equals to 13. Okay, and I will talk about that later on. Okay, so for this video, I just want to highlight the coolness of Pascal's triangle. So I'm going to erase what I have here on the right, and let's try to. Oh, before I do that, we should actually take a look at some other patterns that we see here. Okay. So let me highlight a few other patterns, right? A few other patterns that are more subtle, which I'm hoping you guys can pick up from this video. Cool. So we already know that the coefficients, we can get that from the Pascal's triangle, and that's cool. But what else do you see here? If you look at the power here, the power. Okay, so for the power that the variables with power of 1, I'm going to write them out again just to show you guys the pattern. So this is my first term, right? And I'm going to start out the term with the highest power, which is 3. And then what happens to the exponent? Start with the 3, next becomes a 2, and then I have a 1, and then it disappears, right? And what about the y, the second term that we have here, that we are expanding here? In the beginning, there's nothing there, so I can say 0, and then power of 1, power of 2, and then power of 3, right? So, in other words, the first term is going to start out with that power, and then it's going to drop by 1 every time. Eventually goes away. And for the second term that we are expanding here, it's not going to show up in the beginning, and then it's going to increase by 1 until we hit the maximum. Okay? Also, if you look closer, the total exponents here is 3. The total exponent here is 3. The total exponent here, 3. The total exponent here, 3. So that's another pattern. The exponents, they should add up to whatever we have here that we're expanding. Okay? So please rewatch this section of the video, because these patterns that I'm describing, they are critical. Okay? They are really, really important. So I'm going to show you guys another example using the Pascal's triangles to help us out. And before you do that, before you watch that section of the video, please make sure you know what I'm saying, the patterns that I'm describing here. So feel free to rewind, okay? All right, let me show you guys another example. So I'm going to erase the stuff that I have here. And the example is going to be a little bit more challenging because now that we know the pattern, it's actually pretty easy. So let's say if I have a plus, let's say instead a minus 2b to the power of, say, 5. Yeah? Okay, so which means I'm looking at this row of the Pascal's triangle. So I'm going to have a to the power of 5, right? Plus, and now I'm going to have a 1 in the front, but I don't have to write that 1. Plus 5, because the 5 is from here, times a to the power of 4. Now, I have reduced the power by 1 here. So my second term, which is negative 2b, so negative 2b is going to have a power of 1. And then I'm going to have plus 10, which is from here, the 10 there. A to the power of 3, negative 2b squared, right? So again, 4 dropped to 3, and 1 became 2. Okay? Let me erase that. Not done yet, almost. Plus 10a squared, negative 2b to the power of 3. That's from here, the 10. Next is the 5 there, so plus 5a to the power of 1, negative 2b to the power of 4, and finally plus the 1, which I'm just not going to write it. A to the power of 0 is also a 1, so I have negative 2b to the power of 5. Okay, so I can further simplify this whole thing. I will have a to the power of 5. So negative 2b to the power of 1, that's just negative 2b. So I will have 5 times a to the power of 4 times negative 2b. That gives me negative 10 a to the power of 4b. Plus, okay, let me dismiss this. Okay, plus 10a to the power 3. This will be 4b squared plus 10a squared and negative 8b cubed. That's this one right there. Okay, I'm just simplifying here, and then I'm gonna have plus 5a. That will be 16b to the power 4. And finally, I will have minus 32b to the power 5. So I can further simplify the stuff that I have here. A to the power 5 minus 10a to the power 4b plus 40a cubed b squared minus 80a squared b squared plus 90a b to the power 4. Is that right? I think I messed up a b over here. This should be b cubed. Yes, this should be b cubed. Nice. So 5 times 16, that's 90ab to the power 4 minus 32b to the power 5. Okay, so this is it. If I expand this stuff that I have here, and I will get this whole chunk over here. So you can see how easy it was using the Pascal's triangle, because I know I can get my coefficient 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, 5, 1. Right? And then I just have to be careful with my exponents. And that's it. Right? That's it. Be careful with your exponents, okay? Especially when there's a negative base odd exponent will give us a negative. That's a very common mistake made by students. So if you just check again, you would have A5, A4, A3, A2, A, and then A disappears. No B, starts with no B, and then you have a B to the power 1, B2, B2, B3, B4, and all the way out to B5. That's it. Please feel free to rewatch the second example. It's a little bit harder than the first example that I show you. And I will see you in the next video. Bye bye.